Okay. So I promised you to tell how I shot it in my second book. Okay. So I know that I told you what happened with the sliding mode control. So that I was happy. Professor asked me not to do sliding mode control itself. He told sliding mode control for itself is helpful. You should take care of the illness. And the illness is so I started. So what is the illness of sliding mode control? So is it possible to avoid it? Not. So what you need to do? You need to tell that I need or to adjust it, or told to myself, okay, it's impossible to do something which is maybe not sliding mode control, but looks alike and allow you to deal, to be more or less robust without. So that is why I will tell you how first of all sliding mode control works. And we are telling that. So the point is that point number one. You have tracking error. You need to reach it. And then let's go forward. You have tracking error. You reach it near to zero, and then the system starts. No chance to reward. So that is why what do you need? There are two things. If you'd like to keep sliding, you need that your gain follows perturbation. You don't know perturbation. So what to do? You need to put here adaptive gain. If you would like to keep perturbation, and this perturbation, this alpha should be more or less near to your perturbation. If it will be so, you will have less possible chattering. Okay? Is it clear or no? I need to follow perturbation. I need to follow what I don't know. So how to do it? Let's grow up the gain. And if your perturbations are bounded, once you will reach like that. If it is so, it is not mathematically correct because the perturbations could be such a bit as myself, because you can tell, okay, they are bounded, but the first thing, the perturbation will be around 1, then they will die, then around in 10 seconds, in 100 seconds it will be 3, and 1 million seconds it will be 4. In infinite time, you cannot know in advance the upper bound, and that's one of the hypotheses. But at least, what do you know that if you will grow up the gain continuously, so if you suppose that your perturbations are bounded, you will reach it. That's for sure. The other story, if you will lose it or not. That's the second. So, in reality, there are two questions. Question number one is if you are able to reach and how to reach. Question number two is how to cope. So, first idea was very clear. Let's go with that. So, okay, you will reach it. Your policeman will beat a couple of times, your enemy. And they will still beat it, or with very small, with very strong force, but the perturbation will be there. So that is why what you need to do what? You need to understand how to focus. And that was the key idea of my teacher. He told me, I will grow it up. And when I reach it, I will put it in front. And so, and I will filter out this story. I will filter it out with the error. Because filter is a penguin. You want or you don't. If there is an error, you want or you don't. What I will do, I will pull this alpha like this theta plus some delta, which will be not big. So, and I will follow in some corridor of perturbation. Of course, I will put here the models. But it is clear. So, and this delta should be big enough in order to avoid the escape, fast escape of the story. And it is the simple solution. Okay. And it is written in his book, one of the chapters. You can find it, 93 books. Then he's done it for super twisting as mathematical error, but everything. 2013, it was automatic. So, but the problem was what to do more. Because, let's say, you have puzzling and you will still have a challenge. So, what to do? You see here. Here I'm telling, okay, problems, reaching phase. Then, so, what you are doing is increasing the gain. What you will have gain over solution. Okay? Now, you never know if it is already done or it is still not, because you don't know when you will reach it. So reaching time is uncertain. So we will increase the gain and we will control the reconstruction. We will need low pass filter. So what was an idea? Second idea, and it was a final issue was especially if was Professor Spacey. So, 19, but it was the second idea. The second idea, okay. In reality, let's do the following. let's decrease this again, increase this again, and we'll reach sliding mode. And start to increase again, because the chat is till the moment you lose it, then grow it and then lose it. It is middle term solution, I don't like it, but that was my friends, others were able to do. It's increasing. This problem was not solved. And you are still, if you are losing sliding modes, you are still don't know where you are. And how far you are going outside depends on the perturbation. So, as a result, it was a bad solution. Why bad solution? Because, first of all, you know where, when you don't know when you will stop, and you don't know in which vicinity you will be, because you don't know the upper bound of that solution. Bad solution. That's it. Solution, but bad. So that is why it was a starting point. I was full of this idea, and so what was for me a starting point in this new line of investigation? So uncertainty of reaching time, the bound of the state is not, you cannot predefine. And nevertheless, what you are doing, you are asking the system to have sliding mode and to lose. So you will use every time you will have chatting, and you will overestimation of the gain, which means that you will lose plenty of energy. So that is why. What I was searching for, I was searching for uniform reaching phase. I will searching for absence of chattering, and to close this gap of into the gain, into the adaptive sliding mode control. I've introduced in 2008 together with my authors, my students, French student, let's say, he's not a Frenchman, he's now working in Oman. Even he has position in French, in France, Hussein Abid. And then I will speak about applicability. Because theoretically it looks good, but the point is how to apply it. So let's speak about the following. What's sliding mode? This means that you have sliding modes, and you have beauty and all of the problems. Okay? Now, what people are doing to adapt. What required. They are making preparation. So if you will make it in this way, you will have all, it is linear, and you will have all of the problem of high gain. Because the barrier, the set is small, so the gain is big. And so this means still big chattering. So, and that's what I started for. We've introduced so-called barrier function. It is something like that. And here is, so, what was the idea? The idea was to avoid shattering, but to ensure that you are here in the barrier, inside of the barrier. So, and what is the first lemma? You publish. The first lemma is telling. Okay. If you know, if your perturbation will be bound, there are two things. First of all, your control room. And second, you will be in more smaller set than barrier. Therefore, each bounded perturbation, there is a smaller set you will ensure to be positively invariant set, and you will use finite control. So, bounded perturbations, bounded control, and smaller set. That was the only story. But, and that was the first paper. It was a basic of his PhD. Now, first question people are asking. Hi guys, you are good, but what happens with the noise? Because if you have noises, so the cat is outside, even the cat is preserved, the mouses are dancing. So, it sounds very interesting story, because what we are able to prove. We were able to prove that all depends on the noise. First of all, we were speaking about bounded noises, because you have to understand that any person doing control, which would like to show his high education, he will talk, oh, have you considered Gaussian noises? Have you considered random noises? Easy guy, you are well educated. The question is, have you seen a real sensor? Does it give you infinite signal? What? The signal is every time bounded. And the only data you have is what your provider gives you. And if provider is trustable, he will give you the precision of his equipment. And maybe he will fulfill. Not normally fulfill. But if he is able to give you mathematical expectation of, let's say, the quadratic estimation of his noise, the data of noise, he will never give. The only trustable story is more or less trustable story is precision, isn't it? Is it clear? So that is why what we was considered. We have considered the bounded noise, not stochastic. We have considered deterministic noise. If you have deterministic noises, it is good, but it is not all. Because if the noise is deterministic, even that, if it is discontinuous, means it can make a jump. Your system is wide. If you have a jump, you cannot do more. But if the noise is continuous, what happens with the barrier? Barrier slow down, but you will not lose. But you need to have certain relations between the size of the barrier and size of the noise. relation size of the body and size of it is more or less recent data, 25. So then what we have proven is if the noise is limited, you don't need any restriction because what does it mean limited? The continuity is bounded, so it will work. The barrier will be down, but you keep with respect to your measurement. Near to your measurement, you will be there. That's what it's called. So, you will ask me, Professor, this is a beautiful story you are telling us. But if we have a discrete measurement, every time we can approximate it with a fixed function. So don't worry, guys, if you have discrete measurement, just suppose that real noise is taken. So it will work. So you can every time approximate it. Okay? Maybe it will be big down, but then next story. The next story is also more or less the same. The next story is what we will do. What happened here? We can do different curves here. I've told you that at least what we know that we will have bounded set inside. So, and one of the questions is what will be final set with respect to, you see, if we will start inside, we will go to blue set, which is my final set. Maybe not in final set, but we will go there. So that is why if you need precision, how to choose for body. And so you see, we consider all of the set of the curve, like which could be seen as a homogeneous with this. And we've made an estimation of final set, saying, okay, would you like to have more precision? By it, you will have less final set. Here, there are formulas. Okay? So, then we published a paper in control methodologies in which we made experiments with both. And then the recent one, yes. What we've done, we've told, okay, what, how to find the steps for realization. Because imagine that you are measuring not too fast. So here you have small set, for sure not. So there is a connection between capacity of your equipment and the capacity of noise. the size of noise, the size of perturbation. So if you have perturbation, you have to, you don't know the upper bound, you don't know perturbation. But what do you need to suppose that upper bound is on your upper. That is why step you don't know perturbation, you should base on capacity flow. And so with this, you can tell which step you have to use. And then it is possible to realize. What we are telling here is the following. In general case, when you don't know nothing, your system is blind during the step. Because it's blind, because the system changing, you don't know what happened. So you have to do this. That is why I'm telling to all of you, please, if you'd like to continue to work with me, please make me at least an option to measure the signal, because otherwise I will be blind and you can go out. That's the story. It happens like this. So the first lemma we proved that in general case it doesn't work. So the second lemma we proved is okay. We have to understand how to choose the gain based on capacity of your state. That's how it works. So, and you see, finally, what we are able to ensure that we are able to estimate the final test, and we are ensuring it in the presence of it. So, and this is the last step. I'm not sure that it is already published. It is under consideration tonight. It is precisely how adjust altogether. Final set and in distance time. So, and that's what has been done. You see, here we've considered all of the set of controllers uniform, finite time, and we are taking maximum from both of them, and we are telling how to define the steps in order to realize. Okay? That's more or less clear, let's say, simple explanation of all of the story. So, graphs and so on. Just to make the story, to finish the story, show you a video which has been realized precisely with this type of controller. This one, it is precisely this way. So we are doing it. It is the system with two degree of freedom. you were able to write in two stories. So that's more or less how it works. Why I'm telling that, and I'm not sure if I it's good to show it here, but this is the story. I would send the Professor Fuller congratulations with his birthday. So, thank you.
Sorry, I think the class, we have to, we can close.
Okay, we can, yeah, it's good.
Okay, thank you, sir.
But I don't know if I will give you the presentation before.
Yeah.
Well, the very recent publication, why I told you that I'm sure that because I put the control without check. But it is not sliding on control itself, because it doesn't keep sliding. Just a corridor. I think it is clear.